Greetings, I am Burak Dönmez. I will present the study named Life Cycle Analysis of a Single Family House in Mediterranean. This study is a mutual work by me, Bekir, Enes, Özel, and Nuri, Cihan, Kayaçetin. First of all, I want to show an outline. The presentation will start with an introduction. Basic background information will be provided in this section. After that, in the method and material parts, goal and scope and data sources of the study will be reviewed. Then, impact assessment, analysis of the scenarios, discussion on the LCA tools part will be presented in the results and discussion topic. And finally, a conclusion will be drawn. When construction, operation, and maintenance activities included in the calculations, buildings are responsible for approximately 40% of the energy demand and 45% of the global carbon emission. In this respect, it is important to consider both embodied carbon and operational carbon as a whole. For this purpose, the life cycle assessment methodology, LCA for short, is being adopted by construction industry since 1980s. This way, the energy spent in the production, transportation, and installation of the building would also be included in the calculation. In this study, the environmental impacts of a single-family house were assessed according to LCA methodology. It was aimed to test the effects of natural and local materials in the life cycle of a single-family house building. Main goal of the study is to compare the effects of different buildings, building materials, and construction techniques on global warming potential, which is calculated based on the carbon dioxide emissions. For this purpose, it was decided to investigate a single-family house project in Bodrum, Turkey. Three different scenarios were designed for comparison purposes. A secondary goal for the study is comparison of two LCA tools. One-click LCA and Athena impact estimator was chosen for this comparison. Results from them are compared with each other. The model of the house can be seen on the slide. The house has two stories without a basement, has a flat roof, and gypsum board interior walls. Double glazed with aluminum frames is used in the windows. The interior doors are hollow core wooden doors and exterior door is a steel door. The building is settled in a 6 meter to 15 meter rectangle area. The gross internal area of the building is 180 meters square and the net internal area of the building is 140 meters square. The three scenarios can be seen on the table. Scenario 1 has a reinforced concrete frame structure. Its exterior walls are made of an AAC coated with plaster and paint. It has rough wood installation on exterior walls. The columns are placed inside the interior walls on two longitudinal sides. Scenario 2 has straw bale units and structural system at exterior walls. These units are coated with clay straw plaster. Scenario 3 has stonemasonry load-bearing walls, a structural system, and exterior walls. The stones used in these walls are assumed to be gathered on site after an excavation work related to another construction project. These walls are left uncoated. LCA stages included in the study can be seen on the table. The main data sources of the study are database of Athena Institute and one-click generic construction material database. Where they fall short, data from other databases included in one-click LCA, local APDs from APD Turkey, and APDs from manufacturers are also used. The figure on the slide shows the total GWP of the building throughout its lifetime. Results from both LCA tools are drawn in the figure. Blue bars are results from impact estimator and the orange bars from one-click LCA. As you can see, results from different tools are quite similar to each other. The second graph shows all the embodied carbon emissions. The difference between scenarios are more visible in this one. You can see a sharp difference between two tools on the scenario 2. It is mainly because one who doesn't take the carbon absorbed by the plant-based materials like straw bales and timber while impact estimator does. This difference also shows how important the afterlife scenario is for the plant-based materials. Because if these materials are burned after their lifetime, all the carbon absorbed by them will be thrown to the atmosphere. The difference caused by different afterlife scenarios for the straw bale units can be seen on this graph. On the left bar, the straw bale units are properly downcycled, while on the right bar, they are burned. The difference is striking. There are several points that can be discussed on the outputs. First of all, operational carbon emissions, which is shown as B6 in the graph, clearly account for a vast majority of the total emissions. Even though the amount varies between the scenarios, operational carbon emissions are responsible for the GWP than any other life cycle stage. As an example, global warming potential of different life cycle stages of scenario 1 can be seen in figure. It was seen that scenario 1 has significantly higher embodied carbon than the other scenarios. This situation has two main reasons. The first reason is the material preference for exterior walls. In scenario 1, the exterior walls are made of AAC blocks. The production and transportation of these blocks account for a significant amount of emissions. On the other hand, scenario 2 has straw bale wall units. These units have net negative carbon emissions due to the carbon absorbed by the plant-based raw material. Scenario 3 has stonemasonry walls that are obtained from a nearby excavation. Therefore, they are assumed to have zero production and transportation emissions. Comparison of the effect of the exterior walls can be seen in the figure. The second reason is the structural system. Scenario 1 has a reinforced concrete frame structure. Even though the concrete material has low carbon emission per unit, the amount of concrete used in the structural system is significantly larger than other materials. As a result, reinforced concrete frame system causes a very high amount of carbon emission. It was seen that the embodied carbon of scenario 3 is the highest. As vertical load-bearing elements, scenario 2 and scenario 3 has the exterior walls. In the case of flooring and horizontal element, both scenario 2 and scenario 3 has glulam beams and timber joist slabs. Due to their relatively low amounts, they have a smaller effect on the total embodied carbon, and they perform better than reinforced concrete floors in terms of carbon emission. Thus, embodied carbon is lower for scenario 2 and scenario 3, as can be seen in the figure. To conclude, we can say that life cycle assessment is a crucial methodology for a holistic operation to sustainability. In this study, the comparison of the LCA of three different structures is executed. One of these structures is reinforced, the others are structures made with natural and local materials, which are straw bale and natural stone. The results show local and natural materials perform better than synthetic materials that are transported from different locations. It is also discussed that afterlife scenarios are crucial for plant-based materials. The analysis also includes embodied carbon and operational carbon separately. In addition, these life cycle analyses were performed in two different software and their results were complete. These are the references for the study. Thank you for watching.